Hello everyone, welcome to the 7th session of the QFD. Today we are going to talk about three concepts about Dirac field. We're talking about Dirac Lagrangian, the angular momentum and the spin, and manifold and a spinner. So the third concept is going to explore the concept of the manifold. Maybe it's not really um, something relevant here, but it's a very interesting argument to see how, in general, the vector transformation works when we have a geometry or a gauge field. And in the future, we will see how the gauge field and geometry are similar things, and general relativity can be connected to the concept of the gauge field in a way. Okay, so now I'm going to start with the Dirac Lagrangian. So what is the Dirac Lagrangian? We didn't talk about it. So the Dirac Lagrangian is equal to psi bar of x, and then we have the Dirac operator here, similar to the Dirac equation, and then on that side we have psi of x. So this is a scalar. This is a scalar, and I have to define what is psi bar of x. Psi bar of x is psi dagger of x, but there is a gamma 0 here. So this gamma 0 is kind of interchanging the upper and the lower index. So we're going to see why we have this bar definition because of some normalization consideration. So let's see. We had u of p, and the u of p, we defined it in the last session, is equal to square root of p dot sigma, the square root of p dot sigma bar acting on psi. Okay, and then I could really construct u dagger of p is equal to psi dagger p dot sigma and psi dagger p dot sigma bar, and then the u dagger p times u of p. So this is just something like inner product to get a scalar out of these two vectors is going to be psi dagger p dot sigma psi plus psi dagger p dot sigma bar psi. So here we have psi dagger psi p dot sigma plus p dot sigma bar, and this is going to be equal to psi dagger 2e of p sigma 0 psi, and this is equal to 2 psi dagger ep psi, and that's something that has the energy factor inside of that. So this energy factor here make it not Lorentz invariant. So we don't want that. So how to do that is to involve this gamma 0 in that study. Now I'm going to do u bar of p is equal to u dagger of p gamma 0 right now. So then I have u bar p times up is equal to the same thing here, p dot sigma bar, but here there is a gamma 0, and then I have p dot sigma psi p dot sigma bar psi, and then this gamma 0 is going to flip this order because it is like this. So there is like two unitary matrix here, and it can flip the upper and lower index. So the final result would be psi dagger square root of p dot sigma bar psi plus psi dagger psi square root of p dot sigma bar p dot sigma. So the final result would be psi dagger psi p dot sigma times p dot sigma bar, and this is equal to psi dagger energy. So that would be energy times sigma 0 minus p dot sigma bar. Actually, there is a factor 2 here. Sorry, because we had the summation of 2. So we have summation of these 2. So there is a 2 factor here. And now the inner result is going to be m squared I, or unitary vector psi. And now we have the rest mass here. So this rest mass is invariant under the Lorentz transformation. And that's why now we need this gamma 0 to flip that order to create these terms here, p dot sigma times p dot sigma bar. Because this is going to make e squared minus p squared is equal to m squared. Okay, so that's the reason. So anyway, the Lagrangian is going to be psi bar of x, the Dirac operator minus m psi bar. And just to mention, the derivative of Lagrangian with respect to the derivative of psi bar, any derivative of psi bar is equal to 0. So the Lagrangian doesn't have explicit dependence on the derivative of psi bar. But this is not the case for psi. And we're going to see how is it going to be useful in the next calculation. So the next concept is angular momentum. So we have the angular momentum. And I specifically want to talk about how orbital angular momentum is not equal, but basically equivalent to spin, because that was one of my questions always, that how a spin is related to angular momentum. So in general, the idea is that the spin has a similar algebra to angular momentum. So they are the same thing, but it's interesting to just go to Dirac field and see how the definition of the spin and angular momentum can create some conserved current, and we call it total angular momentum. And we're going to see how this total angular momentum is conserved. So imagine that if it is really hard to imagine what's the spin of the field, so we know about the spin of the particle, but imagine I have a box here, and this box is my universe, and then I have some content here. I have psi, and then in the blue I have psi bar. So these two independent fields. And my question is that, is there any field that I can use to describe the angular momentum, the spin? So I mean spin at point x or angular momentum at point x. And is there any way to measure that? So the question is, of course, because we have energy content here. And as far as we have energy content, we basically have energy momentum. And when we have momentum, we have angular momentum, but for a differentiation of space-time. So imagine this content here has energy, and this energy is equal to momentum, and this is R, so R cross P can produce the angular momentum for us, but with some considerations here. So I basically had the symmetries on the Dirac Lagrangian. It's easy to prove that Dirac Lagrangian respects the very basic symmetries such as translation in a space and time. So let me say I have symmetry in time translation that is equal to energy conservation. Similar symmetry in space is momentum conservation. And I had this also symmetry here, symmetry in space, let's say rotation. And rotation is different from translation. That is equal to angular momentum, so orbital angular momentum. Let's say we expect this argument to give us that orbital angular momentum conservation. And the last concept is symmetry in space time generalized rotation, which is the Lorentz group. So we are saying boost plus rotation, and boost here was giving us a spin, and this is giving us angular momentum but orbital, and together they're going to give us total angular momentum conservation. Now the question is how to find angular momentum and how to find a spin current, let's say, and show that the change of those currents are equal but with the opposite side, so that's how we can say the total summation of them is different. So let's go to first the orbital angular momentum. So for the orbital angular momentum, we need to define the general definition of the angular momentum. The general definition of the angular momentum is that angular momentum is constructed from x cross p, and we know p in the quantum field language has t mu nu, so it has two index, and here we have x, let's say lambda. So when we have outer product, then we are making a 3 index entity. So I call it the density of angular momentum, right? So T mu nu we calculated for the Klein-Gordon field, but the principle is similar. It's about a space and time translation is equal to the derivative of Lagrangian with respect to with respect to the muth derivative of psi times the muth derivative of psi, so that's the field deformation plus the derivative of Lagrangian. Similar calculation for psi bar and the muth derivative of psi bar here on that side, because psi bar is a dual vector of psi minus g mu nu of Lagrangian. So now I'm going to calculate this term here. As we said, this term is 0 because there's no explicit dependence of the derivative of the psi bar on the Lagrangian. So I have this term here. This term is going to be equal to I psi bar gamma mu. So this is coming from Dirac. This is coming from the Dirac Lagrangian. So if we are just taking a derivative from the muth derivative of psi, it's going to give us some psi bar because there is a psi bar on the other side. So now the final answer is going to be I psi bar gamma mu, the nuth derivative of psi plus minus I, so let me go down, minus I g mu nu. Now the Lagrangian is psi bar I. Now I have to say omega sigma, the sigma derivative, minus m psi. So that's the energy momentum tensor. So the energy momentum tensor is equal to I sigma bar gamma mu, the nu derivative of psi, minus I g mu nu sigma bar I sigma gamma of sigma minus m sigma. Okay, so now I have the energy momentum tensor, and then I go to write down the derivative to definition of the angular momentum tensor. So the angular momentum tensor of mu nu, lambda mu nu, is defined as x mu t lambda nu minus x nu t mu lambda. So that's a generalized form of the outer product of x times p in order to preserve the anti-symmetric nature of this outer product when we're going into the tensor language here. And now I have the derivative of lambda of L lambda mu nu. So we are just taking derivative with respect to lambda index here. That's a space-time. So that's a space-time, or, is this x coming from this x? It's a space-time index. So we're taking derivative with respect to that, and we're going to have the following expression. So the first term here is going to be delta mu lambda t lambda nu. The other term, so the first term here, the other term is going to be x mu t lambda nu minus delta nu lambda t mu lambda, again minus x nu derivative with respect to lambda of t mu lambda. Now we have these two terms here similar, and then these green terms here. These green terms are going to be equal to 0 because of energy momentum conservation. So the final result is going to be, so this delta here is going to just change the every lambda with nu. So it would be t mu nu minus t nu mu. And in general, we can't say this expression is equal to 0 unless we know t mu nu is equal to t nu mu. But we're going to show that this is not the term. This is not the case here. So we're going to show that this is not the case. So I have t mu nu is equal to, I have this expression here. For that. And then for the case of nu mu, I'm just going to change the order of parameters. But the sigma in this should not be interchanged. And these two terms are going to cancel out each other when we subtract them with the condition of g mu is equal to g nu mu, which is in general correct for a good metric, or I think a correct metric. So this term here is correct. So this term, the second term, is going to cancel out. So t mu nu minus t nu mu is equal to I psi bar gamma mu nu. And now we're going to show with the trick that this term is somehow equal to the definition of the spin change. How? We're going to go to the Dirac equation. So now we're going to go to Dirac equation and replace this term here with minus m im gamma nu psi. And our purpose is to get rid of this derivative and replace it with this gamma matrix. Because I have a gamma matrix here and I want to kind of play with them. And we have the similar replacement for this one, for psi, which is equal to minus im gamma mu psi. Okay, and now I'm going to write down this term. This is equal to, so there is some I here, we need to be kind of careful. This is going to be m psi bar gamma mu gamma nu psi minus m psi bar gamma nu gamma mu psi. And then we are going to have psi bar, m outside, psi bar psi. And here we have the commutation of the gamma matrices. So gamma mu gamma nu, And then we set the definition of the generators of the spin rotation. So if you remember, we had this from the last session, we had this sigma mu nu, which was equal to I over 4 commutation of gamma mu gamma nu. So this commutation is going to be equal to 4 mi sigma mu nu. So at the end of the day, T mu nu minus T nu mu is equal to 4 mi psi bar psi sigma mu nu. So this is the angular momentum. So this is the orbital angular momentum here. And now the next step is going to calculate the spin current change, the change in the spin current. Okay, so the spin current is also going to be defined as something with the 3 index here. The spin current is going to be S lambda mu nu, and we are going to define the Noether's theorem. So based on the Noether's theorem, this is going to be the derivative of the Lagrangian with respect to the lambda derivative of psi. Now the generators of that rotation, which are those sigma, as we talked about it in the representation. These are the generators here, or these are the deformation of the field, plus the next term, which is the similar term, but this time for psi bar, sigma mu nu for psi bar. And again, this term is going to be 0. And this first term is going to be I sigma bar gamma lambda. Okay, and now it's going to be I sigma bar gamma lambda sigma mu nu psi. And this is going to be S lambda mu nu. And then let's calculate the derivative here. And it is like a kind of maybe for the conventional reason, we can redefine the spin current as S goes to IS. So we are going to add one extra I at the end to the definition of the spin. So spin current is going to be S lambda mu nu is going to be minus sigma psi bar gamma lambda sigma mu nu psi, because we're going to add this extra I as a conventional reason. And maybe this I is a connection between the angular momentum and the internal space, because internal space is 2-dimensional. And this extra I is bringing those extra way for us to rotate something 3-dimensional in the 2-dimensional complex space. So now the derivative of the spin current is going to be equal to minus the lambda derivative of psi bar gamma lambda sigma mu nu sigma minus psi bar. Everything is the same, but now we're going to take the derivative of psi. And then we are going to use, again, from those identities that we found in the Dirac equation. So I want to get rid of this derivative of this field, right? So this is equal to psi bar I m lambda of, gamma of lambda with the with the lower index. And here I have minus I m gamma of lambda sigma, and they came from Dirac equation. Dirac equation, you can say Dirac Lagrangian, but I mean Dirac equation because we have explicit term for those. And then I'm going to have now minus I m psi bar gamma lambda sigma mu nu psi plus I m psi bar gamma lambda sigma mu nu gamma lambda psi. And this term is going to be 2i, 2 unitary matrix. So I'm going to have minus im psi bar. So I'm going to take 2i sigma mu nu psi plus im. And we have an identity here. It's a little bit long algebra to really prove that, but this is going to be minus 2 sigma mu nu when we have a sandwich of the generators of the spin rotation between the gamma matrices, and a specific algebra makes it like that. So I'm going to have im psi bar minus 2 sigma mu nu psi, and then I'm going to have minus im psi bar sigma mu nu. So there is a 2 term here. Plus 2 sigma mu nu psi. And then I'm going to have minus 4 im psi bar sigma mu nu psi. And that is equal to the derivative of the spin current. So now I'm going to have the derivative of the total angular momentum, or J lambda mu nu, which is equal to the derivative of spin current plus the derivative of angular momentum current. This is equal to minus 4im plus 4im psi bar sigma mu nu psi is equal to 0. So, and then we're going to see total angular momentum is conserved. Oh, but with this conventional redefinition. Okay. Now, we talked about how a spin and angular momentum are behaving the same, and how these currents are conserved at the end of the day. The last thing I want to talk about is the manifold. And in the last sessions, we faced this question of what is the definition of a spinor. So spinor, what was a spinor really? We said if we have a transformation, for example, imagine that I have something x and it goes to, let's say, omega x, and this omega is infinitesimal boost rotation or anything like that, then my psi is going to be some s of omega over psi, right? So this is a representation, and we said how one SO3 is going to break down into SU2 times SU2, and this is called a spinor transformation, and a spinor transformation act on a spinor. And this spinor is not something like a space-time component, but this spinor is breaking into 2 independent blocks, and one of them is left-handed and one of them is right-handed, and that's how they transform. But to understand the meaning of a spinor, we also need to talk about something that is called parallel transformation, parallel transport, or covariant derivative. That's a subject in tensor physics and GR that comes very handy, and actually connects the gauge theory to GR. It's a similar concept, and talks about how to transform the vectors on a manifold. So imagine I want to talk about manifold. What's the definition of the manifold? So manifold is some set of space or time points, or in general, mathematically, manifold is a set of points. So there are so many points on a manifold. And the smooth manifold in general, a manifold that you can really define a very smooth structure on them. The definition of it is that at each of these points, you can define a tangent hyperplane. It depends what dimension it has. So imagine if the dimension is n, the dimension of this hyperplane is going to be n minus 1. So if your manifold is one-dimensional, like a curve here, at each of these points, you have those tangent planes which are tangent lines, and these tangent lines are kind of separated islands from each other. The definition of the manifold is that if you choose any of those points, and if you try to increase the neighborhood of that point, you would be able to find a Gaussian coordinate, or a flat metric, or maybe you can say Minkowski spacetime. Or something which is locally flat, and something which is locally flat, and you can use flat coordinate to label those areas. So imagine I have this manifold here, and imagine that each of these points I have an area that I mark with red here, and I call it A, that is basically this entity is seeing it as a flat spacetime. And then I have this yellow area, and I call it B, and this is for the other point. This is the neighboring point. And imagine in a scenario that there is an overlap region between them. And in the overlap region, imagine that I have coordinate system that I call it x1 here, and I have a coordinate system which I call it x2 here. And there is a connection between x2 and x1. So x2 is equal to f of some x1, right? And this function here is how these coordinates are mapped. So if there is a function, I mean, if you can define a manifold, you can define these manifolds here. You should be able to define this function. And that's the definition of a smooth manifold, that you can define these kind of functions that you can infinitesimally take derivative of them and let them have a good definition. So if I take the nth derivative with respect to any coordinate, that should be well defined. So if it is well defined, as we think space-time around us is well defined, there is this transformation between these two coordinates. And then the point is that if I have a vector here, and if I have a vector here, so imagine that now I have a vector field defined here. I define a vector field here. So I can define vectors inside of that. How can I really transform this vector field into point B and really try to understand how to compare it with the vectors living in the patch B? So I need to take this vector from here to here, and how theoretically is doable is it's called this representation transformation. So imagine that I have this patch A, and I have this vector here. So imagine that I have this vector here that I show with, let me draw another manifold, and I have this patch A, x1, and I have this patch B with x2, and then I have a vector here at patch A. So what I have to do is to take these vectors into this intersection area, and it would be a parallel transport because A is flat. So A is flat. So when I define the vector, let's call this point x1 and the intersection point called x prime 1. So when I take x1, I take it to the v of x1 prime, v of x1 prime dot v of x1 is equal to so because these two vectors are parallel, this inner product is equal to, let's say, v of x1 squared. But this is not equal to 0, right? And then I have this intersection area. So imagine that I have a vector here, and then I have this vector here, and then I have also the function to map this coordinate. So x2, this is called x2, or x prime 2 is equal to f of x prime 1. And now the v at x prime 2 is equal to some s of f. So that's the representation. And this f is a function to transform these coordinates acting on v of x prime 1. And now if I calculate the inner product of x prime 2 time dot v of x prime 1, I'm going to have some cosine of theta, and that's the rotation because of some intrinsic property that it is decoded in the coordinate transformation. For example, if I have this coordinate transformation between x1, x2, any function can define some geometry or curvature or even gauge field in many cases. But here, just thinking about geometry. So the geometry can be decoded into those transformations. So these vectors are, when we are moving them into another point of a space-time, they might rotate from their original direction, and that's because, and that's a cosine of theta, and that's because of some curvature here. And this curvature is encoded into these manifold mapping. Okay, so why did I say all this story about manifold? I wanted to say that some normal vector, something which we call it a normal vector field, when we are rotating it for 2 pi, it would return to itself. So imagine that I have a manifold here, and then I have a vector field that I define it, for example, as the definition parallel to that plane. And imagine I define a closed path, and anytime I say a closed path, I mean something that could be mapped to a circle or 0 to 2 pi. So the parameter here, lambda, is 0 to 2 pi. So when I change lambda from 0 to 2 pi, I'm sweeping this curve here, right? And now if I define some vector field, for example, that it is parallel to this point, when we are moving this vector field here with the principles of rotating them based on the curvature, after 2 pi, the vector is going to return to itself, so in a closed path. So f of 0, imagine, is I, or unitary. So if I really don't rotate the particle, nothing is going to happen to this vector. And f of 2 pi is also equal to unitary. And if something is transforming like that, so when we are rotating it for 2 pi, it's going to return to itself. So it's going to return to itself. And that's a vector. And that's a vector field. A spinor somehow is interesting because a spinor is living on the Mobius. So the spinor is living in the Mobius band. I mean, this is a type of manifold that spinor is living on, and there is a twist here. So I mean, this is not some like ordinary manifold that we are just seeing, but I want to say how it's different from the ordinary manifold. And maybe I should demonstrate this better with the perpendicular. It doesn't really matter if I have even a perpendicular field. So imagine I have this perpendicular field here, and I'm transforming it along this path. And again, when I come back to the original point, I'm going to have the same vector here. So 2 components here, perpendicular and parallel component, both of these. So if I have any vector like that, and if I transform it under the closed path, I'm going to end up in the same direction that I started with. But a spinor is like living in a Mobius band. So a Mobius band is something that it is closed. It's a closed path, but there is a twist here. So there is a twist here, and I can't really draw it right now on this page, but there is a twist here that just flipped the orientation of the field. So imagine if I start from here and transforms these vectors. At this point, when we are twisting, the direction of the perpendicular field is going to change, and it's going to be on the other side. So now I'm going to have this type of transformation. So when I come back to the original point, after 2 pi, I just ended up in the opposite direction. So again, f of 0 is equal to unitary, but f of 2 pi is equal to minus unitary. And that's one of the features of the spinor. So a spinor is living on a Mobius band, and that's why a spinor is a little bit different from a vector. And there is some twist. So when you are rotating the spin for after 2 pi, it's going to end up in the opposite direction of the original point. And I just wanted to say this point of how maybe these concepts are interconnected a little bit, the concept of manifold and how to parallel transform a vector. And maybe we have more time to talk about it when we are talking about the gauge fields. And the gauge fields, we really see how this manifold definition is coming very useful here. So again, we're going to review the concept here. So we define this Lagrangian, and we define why should we go to the definition of the bar, because we want to make some Lorentz invariant term here that doesn't have energy dependence. And then we calculated the angular momentum conservation here using the definitions of energy momentum tensor. And then we calculate the spin current and showing that the total angular momentum is conserved. And then we talk about some about manifold and how manifold and parallel transformation defines a curvature and how to transform a vector. And then we talk about if we are transforming a vector in a closed path, after 2 pi rotation, it's gonna come back to itself. But when we have a Mobius band, so there is a twist point. So any vector is gonna twist at some point. So when we are having this 2 pi rotation, we are not gonna end up in the same vector. We're gonna have the opposite vector. So in the next session we have, so in the QFT 8, we are gonna talk about the quantization of Dirac field. Finally, there's a lot of concept actually about Dirac field, and we need to really study them with care, especially the discrete symmetry. We're going to talk about them in depth. And thank you so much for watching QFT 7. So see you on next session.